Suppose we have some compound. Someone figured out it was 3 grams of H and 24 grams of oxygen. And what we need to figure out here is, what is the formula? It can only work in moles here. And another thing that makes this part become a little bit more straightforward is that if you're working with some common elements like hydrogen, oxygen, nitrogen, things like that, you're going to see a lot of those different types of formulas in this part of the chapter. You may notice if you look at their weights, they're actually really close to a whole number. Hydrogen is about 1, nitrogen is about 14, carbon is about 12, oxygen is about 16. If your mass is close to a whole number, you can go ahead and use that whole number, and it makes your calculation work out a little simpler when you're punching it into your calculator. So what I need to do is convert each of these to moles. After you have every single element in moles, you then want to write a formula using these numbers as subscripts. Now what we do is we divide through by the smallest mole number. So keep in mind that you have to stay in whole numbers here. So whenever you get a final formula, you have to have whole numbers there. You cannot use fractions or decimals for your subscripts. We were given actual gram quantities. Another common thing you're going to see is if you're given mass percentages. So for example, aspirin has the percent composition of sometimes if you add these up, they might not be exactly 100 due to rounding issues, but they should be pretty close. And what I want to do here now is get to the molecular formula here. Suppose you had a 100-gram bottle of aspirin that was exactly 100 grams. Based off the percentages here, how much of that 100 grams is carbon? 60 grams, right? So what you can do is, to make these problems work out, is you assume a 100-gram sample. And what that allows us to do is use these percentage numbers as if they are grams. And then after that's done, you basically approach the problem in the exact same fashion as the previous problem we just did, which I'm going to go ahead and do now. Alright, so I need to figure out moles of carbon. And I'm going to go ahead and write out the whole setup first before I break out my calculator. You then go ahead and write out your formula, C5H4.48 O2.22. I then am going to divide through by 2.22. All right, can I stop there based off what I said earlier about whole numbers? No. So now what I need to do is you need to multiply the whole formula by a factor to get whole numbers. So what do you guys think I should multiply that formula by to get whole numbers? So the problem here is carbon, right? So what can I multiply that by to get a whole number? 4. Yep, so what I'm going to do is take the whole thing times 4. And then what do we get here? 2.25 times 4 is what? 9. So C9H8O4. And doing a little OChem for you guys. This is an organic compound, but you learn how to do drawings like that when you get to organic chem.
Okay, so for this one, same steps as always. So we did that assuming that we had 100 grams. Okay, we'll set up the conversions. We probably, again, that's a good thing to practice. Okay, so after we did this, we set up our compound that has sort of the weird numbers. Okay, we're going to divide everything through by, good, 1.975, 1.975, 1.975. Okay, so when you do that, you get C 2.66 repeating, O, H 2.66 repeating, since those are about the same. So what do we do? Just round up? No, right? We have to, this isn't a 1 to 3 or a 1 to 2 or a 1 to 4 thing. This is going to be something a lot more fun, like a 3 to 5 or something fun like that. So we have to figure out what it is. Okay, so we need to figure out what we need to multiply everything through by to turn all of those weird decimal-y things into whole numbers. So what do you know about, what could you multiply something with a fraction of 0.666666666 through 3, right? That is 2/3. So if you multiply through by 3, that should turn your carbon and your hydrogen into whole numbers. Okay, so 7.999, which is 8, right? So C8, that will make O 3, because again we have to multiply everything through by our sort of factor there of 3, and H will also be 8. Okay, so we had to multiply through to turn those. Just rounding, this we could round, obviously that's 8, but 2.666 repeating, that's not something that we would round. Okay, so the empirical formula here, this. Okay, so what are some of the common fractions we'll see? Obviously we sort of saw, if you have this, this is 1/3, so you're going to multiply through by 3. Okay, so that's what you would multiply through by. We just saw this one here. Same sort of thing if you had the 6's. Again, you would multiply through by 3. So that takes care of the 3. Another one you'll see would be a decimal of course, 0.5, which is 1/2. And then you know you need to multiply everything through by 2 to get rid of the half. Another one probably like the 2/5 and 7/5. And you would multiply through by 4. I've never seen a whole lot of, say, like multiplying through by 6 or 5. Those are a little more exotic. These are the ones you would see more, sort of 2, 3, and 4, where you have 1/3 or 2/3 or a half or a fourth or a 3/4 even. We'll even go ahead and put that in. So that would be our 3/4. So we would multiply through by 4. So again, this column I made here, this is what you multiply subscripts, and this is your decimal. So again, when you see, like we saw here, when we saw this decimal, we knew we had to multiply through by 3. Okay, so that's what that means. When it doesn't divide out whole, figure out what your decimal is and multiply through by that multiplier. So this is actually a real compound. This is called Methyl Salicylate, and it makes the wintergreen flavor in gums and things like that. Okay, so any questions on this?
Let's take a look at glucose. Glucose is a pretty important biological compound. It is a carbohydrate or sugar. And it turns out that it has the following percent composition. I wanted to point out that in the problems that I like to give, you're mostly going to be dealing with carbon, hydrogen, oxygen, nitrogen, because I am an organic chemist, so I will give you organic compounds. And I figured a lot of you guys are probably going into biology anyway, so it kind of makes sense to work with these types of compounds. Your homeworks, though, will have inorganic compounds a lot of the time, but the process is identical. It doesn't really matter if it's organic or inorganic. The process is the same. All right, with that out of the way, one other mention I want to have here is the molecular weight of glucose is equal to 180.156 grams per mole. So what I want to do here is figure out the formula. These problems can become very tedious because of all the writing you may have to do, but thankfully the approach is similar for all of them. All right, so then when you put this together, C 3.33, H 6.71, oxygen 3.33. All right, and then I'm going to divide through by the small one, the 3.33. And you may notice now I end up with a formula that is CH2O. It may appear at first glance that you're done, but in a problem where you're given the molecular weight, you should actually check your answer to make sure that you actually have the right structure. If you have the right formula here, the way this will work out is if I calculate the molecular weight of this, it should match this. So what I'm going to do here is calculate the molecular weight of CH2O. So we have 1 times carbon, 2 times hydrogen, 1 times oxygen. All right, so it's going to work out to be 12 plus 2 times 1 plus 16. And if I add that all together, what do I get? We have 30 here. The problem told us at the start that the molecular weight of glucose is 180, but we're getting 30. So what that tells me is that we did not actually determine the molecular formula, we determined the empirical formula. So keep in mind that these calculations give the empirical formula. We need to compare the molecular weight to get the molecular formula. And I haven't defined these yet, the difference. So the difference here is that the empirical formula is the simplest whole number ratio between all the different atoms. We saw that those kind of formulas when you were dealing with the salts, right? And the molecular formula is the actual formula. It will either be equal to the empirical or a multiple of the empirical. It always works out when we do these types of calculations, we will always get these smallest whole number ratios, which means we are always getting the empirical formula. So if you ever see a problem like this that they're throwing in a molecular weight in there, this is probably what the problem's trying to get you to do. It's trying to get you to figure out if you have the empirical or the molecular. So once again, to summarize, if this number ended up being equal to this number, then we're done. If they're not equal, I need to figure out a factor to multiply it by such that they are equal. So what can I multiply 30 by to make it equal to 180? 6. So the actual, and the way you can figure that out, to figure out this multiplication factor, the molecular weight divided by the empirical molecular weight. So basically what we're doing is we're taking 180 divided by 30, That's equal to 6. So running out of room here. So what I'm going to do for this formula is take CH2O and multiply it by 6. And now I have a proper formula of C6H12O6. All right, so that was our empirical, the CH2O. And then here we have the molecular, which is the actual formula. I mentioned to you guys before that sometimes in science we use words that are technically incorrect, but they were used for so long that they got ingrained into our language so that we still use them anyway, even though they're technically incorrect. The word carbohydrate is one of those words. So it turned out in the olden days, a lot of times the way they would determine these percentages, they would do some combustion analysis where they burn it and they get the pure elements to come off, and then they get the masses that way. They were finding that whenever they burned sugars like this, they always got the formula CH2O. So we have carbon, water, carbohydrate. So they basically lumped them all into this hydrates of carbon they thought they were. And it wasn't until later we actually figured out they're not actually hydrates of carbon, but they have that empirical formula. But hydrates are actually technically different than what a sugar actually is. But even though that's technically incorrect, we still use it because it got so ingrained into our language. So to keep that in mind, that there are words like that out there, and it's okay. Because we now understand that they are wrong, but we still use it anyway. All right.